Hello, welcome back to this channel. And so in these videos, I will be going over the MCAT problems chapter wise, the Kaplan problems chapter wise, right? So today we're going to be working on nomenclature. So in this video, I'll be solving every problem. So the best way I think to approach all of these problems are to maybe download the PDF that I will be attaching below and try to solve those problems. And when you actually have a problem, right, when you're not able to get to the right answer, or if you have to double check your answers, come back to this video and actually then double check your answers, right? Because it's always a good idea to actually do them yourself first, and then, of course, just double check your work and then figure out what your flaws were or what the problem was, right? All right, so hi, I am Dr. Arzu Jabra, and I have a PhD in organic chemistry. I teach organic chemistry as a tutor, and also I am an academic mindset coach. And what that really means is that I actually help stressed out students who are not in a focused state of mind, who feel depressed when they're taking, for example, MCAT, or kind of lost in their academic journeys. So I actually help them bring back on track. I really help you regain your focus, regain your power when it actually comes to the academic setting, and actually help you go closer towards your dream life and not just someone else's life, right? So, all right. And with that, let's get started. So this is the first problem from MCAT. I think what I'm using is a 2022 edition Kaplan. Okay. And of course, I know a lot of these textbooks do not actually have a big difference in the editions. If you do see a difference, feel free to use both the textbooks then, because that will actually give you more practice. But if they're the same, it also helps, because then you can just double check the answers through this video. All right. So for the nomenclature, what is the IUPAC name for the following compound, right? So the first thing to always think about, right, when you're writing actually the nomenclature of a compound, is we usually write the name of the substituents first, and then we write the name of the parent chain. So we'll first write substituents, and then we write the name of the parent chain, right? So now when you actually have substituents, right, so you'll actually find where are the substituents, and you'll want to number the parent chain as the carbon chain with the longest number of carbon atoms, right? And then right now we have two options. So 1, 2, 3, 4, 5, 6, 7, right? Or we could have done the opposite numbering, or we could have started from the left to right. 1, 2, 3, 4, 5, 6, 7. And then, so the second rule applies if from both the sides we're still only getting 7 carbons, right? The rule applies. The rule is actually that your substituents should get the lowest number, right? So when we go from here, we're getting the number 2, comma, so this is 2, comma 5, right? But when we go from the other side, the numbers are actually, I think I've mismatched my colors, but that's fine. From the other side, the number is actually 2, comma, sorry, on the red one, I have 2, comma 5, but on the green one, then I have 3, comma 6. So you want your substituents to have the lowest number. So we are not going to use 3, comma 6. We're actually going to use 2, comma 5, right? So I'll just say 2, comma 5, dimethyl, because this substituent is a methyl. At the second carbon, we have a methyl. And the fifth carbon, we have a methyl too. So this is 2, comma 5, right? Dimethyl. And we know that we want to have a comma between a number and a number, right? And then between a number and a letter, then you would just have like a dash, right? There's always a dash between a number and a letter, or a letter and a number, right? So we got 2,5-dimethyl. So these are the name of the substituents, right? And then the parent chain has 7 carbons. So that would actually just be heptane. Okay. So A is actually the answer for this problem. All right, let's get to the second problem. Or if you're just here, you might want to pause my video and just do it yourself and double check your answer later. That's like another way of doing the same problem. Okay, what is the name of the following compound? All right, again, there are different possible ways of numbering this compound, right? So we can say 1, 2, 3, 4, 5, 6. The good thing about cyclic chain is that you can actually literally start from anywhere. You don't really have to think about the terminal carbon as right as number 1. So you can start anywhere from the middle, from the center, to actually have a number 1. And then on the other side, right? So what we see here, okay, if we started like this, the substituents are getting the numbers 1, 3, and 4, right? So substituents are getting number 1, 3, 4. I want to make sure that I only write that with the red, because this is corresponding to the substituents on the red numbering with the red, what is it called? Numbering of the cyclohexane, right? Now, if I actually did the other way around, so what else could I do, right? If I did 1, 2, 3, 4, 5, I could have done that, and that gives me substituents getting the number 1, 4, 5, which is a higher numbering compared to that one. So that this definitely is a problem, right? That's not like, and that's not giving the substituents the lowest number. Okay, so is there any other way of actually numbering the compound so this compound gets the lower numbers, or the substituents get the lower numbers? So let's think about 1 over here, right? 2, 3, and 4. Okay, if I go this way, this route, 4, 5, 6, then my substituents are actually getting 1, 2, 4. So I do see now substituents are actually getting even lower numbers, 1, 2, 4. So this is actually better numbering compared to 1, 3, 4, right? So, and even other way around, if I had gone 1, 2, 3, 4, 5, right? If I started 1 over here instead of 1 over here, then I would get 1, 2, but then this group over here would have actually gotten 1, 2, 3, 4, 5. This would have actually gotten 1, 2, and 5. So not really, again, big numbers, right? So now you're trying to think like, what is the difference between 1, 2, 5 and 1, 3, 4, really, right? So if you really think about it, 1, 2, 5 and 1, 3, 4 are essentially the same numbers, because the sum of these numbers are really the same, right? So the sum of your substituents, or the lowest locants, should be the lowest, meaning the sum of all of these numbers should be the lowest. So instead of 1, 2, 5, it's all, of course, it's preferred to have 1, 2, and 4, but 1, 3, and 4 and 1, 2, and 5 are actually kind of the same numbers because they have the same sum. And if that was also a situation, I don't think IUPAC's actually going to test you on this versus that. Okay, so now we've got 1, 2, 4. Okay, now if we were to just write the name of this compound, we have the parent chain, which is cyclohexane. And if we actually think about the substituents, so now when we write the substituents, we write them in the alphabetical order. So then we have 4 ethyl, right? Because at the ethyl group, we've got 4. Okay, and then 4 ethyl, and then 1, 1 di, 1, 2 dimethyl. One, 2 dimethyl cyclohexane. So D is the correct answer. And if you were to ask me a question and say, okay, so if I was naming this compound and whatever order I go from, I get the same numbering, right? For example, if this was the compound, let's say I've got a methyl here and let's say I've got an ethyl here, and if I number it like 1, 2, 3, right, versus 1, 1, 2, 3. So in both the orders, right, the substituents are getting numbers that are 1, 3 and 1, 3. So substituents are still getting the same number. Now you want to think about where would your substituent, now you would induce alphabetical order, meaning the substituent with an alphabetical, with a, the alphabet that comes earlier, right, would be the one which actually would be your number one. So this is an ethyl, and that is a methyl. And ethyl in the alphabetical order is a lower letter, right? Like it comes first. So now you would actually use 1 on ethyl and 3 on methyl. So you're now inducing actually the alphabetical order now when your substituents actually have the same numbers. But the first priority is the substituents, and the sum of their numbers should actually be the lowest. The sum of your locants, substituents, should be the lowest. That should be a first criteria. All right. Next, what is the name of the following compound? All right. So now, first thing first, we'll look for the carbon chain with the lowest, or carbon chain with the highest carbons, or the parent chain with the maximum number of carbon atoms. So if I think about it, right? So again, we can go numbering left to right, we can go numbering right to left, or we can go numbering starting over here. But of course, you want numbering in a manner that gives you the lowest substituents and also the maximum number of carbons in your parent chain. And that is why I'm going to choose numbering starting from here: 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I had actually gone here, so I would have gotten 6 here, 7 and 8. If this was my parent chain, I get 8 carbons in the parent chain. But if I go here, I have 9 carbons in the parent chain, and I want the longest chain in the parent chain, largest number of carbons. So that is why this is 9 carbons, right? So this is actually nonane, right? 9 carbons are nonane. So what I see is I do see C and D with nonane. Okay. Now let's think about the substituents. So I have a bromo at the second position, so I can say 2 bromo, right? And then I have iodo at the third position, 3 iodo. I'm just writing down the substituents, and then I will arrange them in the alphabetical order before I put them in front of my parent chain. Okay, so I've got 3 iodo, and then I've got 3 methyl. All right, 4, 4 dichloro, 5 propyl, right? All right, and all I've got to do now is just to arrange them in the alphabetical order. So I'll first write bromo, right? So it'll be 2 bromo, which is actually the same in both the options. The second option is 4, 4 dichloro and 5 butyl. Okay, first things first, this chain is not a butyl chain, it's actually a propyl chain, right? So the option with the propyl would actually be the correct answers. That's the first thing. And then also, if you really think about it, right? So this is important. One of the rules of nomenclature is that when we are again comparing the letters and we want to arrange them in the alphabetical order, right? So now you're actually going to compare B versus C and not really D, right? So whenever we have letters like di, tri, or maybe even tetra, right? Tetrachloro, or maybe trichloro. When you're making the comparison to be able to write your substituents in the alphabetical order, we do not use the first letters. What we're really comparing is the substituent in itself, which is a chloro, right? Which is the C of the chloro would actually be compared. However, so when we do have isopropyl groups, right? Isopropyl, we do compare it starting with the I. We compare it starting with the I, but with dichloro, trichloro, tetrachloro, we do not use, because isopropyl itself means something. It means it's a certain type of a substituent, right? However, di just means it's two of a kind, three of a kind. So then we do not use those prefixes to make the points of comparison. So we've got actually, we're comparing C versus B, and that's why right after B, we've got a C, right? And then I, and then M, and then P. So that's making perfect sense actually. And that is why C is actually the correct answer for this nomenclature. All right. What is the name of the following compound? This is a really good problem. I love this problem. And why? Because now you want to think about two options, right? We have two options to, again, I mean, you'll always have two options to be when you're numbering your compounds. So you can start from here, 1, 2, 3, 4, 5, 6, right? Or you can actually start from here, 1, 2, not one here, but like 1, or actually, never mind, 1 here, 2, 3, 4, 5, 6, right? Or I could have done 1, 2, 3, 4, 5, 6. And my first instinct would be that, okay, there's a double bond and I want to prioritize the double bond in the longest carbon chain of the parent chain, right? However, if you really think about it, we are really prioritizing two functional groups, right? Now, this is like a perfect time. If you do not know the functional group priority, and if it's not on top of your head right now, then this is what you should do, right? Because if you don't have like that priority memorized, if you don't have like logical reasoning of what functional groups actually prioritize and why, when you get a problem which has many functional groups, that would be a problem, right? Then you'd be able to not be able to correctly number the functional group of a higher priority as number 1, right? Right now, for example, here, the two functional groups that we actually have is an alcohol versus an alkene. So if I were to start numbering like from here, then just give me a second, I think. Thank you. So if I were to start numbering from here, right, then I actually, this is number 1, all right? And then alkene actually gets a priority because alkene gets a lower number. However, if I start numbering from here, let's say 1, 2, alcohol gets a priority and alkene does not really get that priority. And if you go back to your textbooks, if you go back to any of your resources, then you'll actually see that alkene versus alcohol, right? Alcohol actually gets a higher priority in the functional group order. And if you're thinking about alkene as a functional group, that's what it does. That's what like the IUPAC nomenclature does, considers everything as a functional group. So that's why the numbering has to go from here, 1, 2, 3, 4, 5, 6. Okay. And now, so what we really have is, so we're saying that we have a total of 6 carbon atoms, so which is hexene, right? And then of course, because it's not hexane, it's an hexene. So we really add the C4 carbon, right? So it's like hex 4-ene. So at the 4th position, there is a double bond, right? So you're telling the reader that at the 4th position, there is a double bond. So we've got hex 4-ene. Okay, now, again, we have to just write, okay, and then of course, so it's at hexene, and also we said alcohol is a priority. So then you have to mention that in the parent chain, of course. So it's not just hex 4-ene, so it will actually be hex 4-ene and 2-ol, right? Because you want your priority to be in the longest carbon chain or in your parent chain. You want the functional group, which is a priority in the longest carbon chain. So we've got hex 4-ene to all, right? And now just write the name of your substituent. So then we've got at the third position, we have a ethyl group. So it will be 3-ethyl. Okay, and then I think trans, we don't really have to think about that. All of them are trans options anyways, and we do see the groups that are higher in molecular mass, right? That's how we compare these. They are opposite to each other, so that's why it's the I think it should more appropriately be called E, actually not really trans, but then because we don't really have a choice, so it would actually just be trans 3-ethyl, right? Trans 3-ethyl hexene, hex 4-ene to all, right? And then of course, if you have 4 over here, you can actually just write it ahead of it. You can just write it in the front, which is totally fine. So you've got trans 3-ethyl 4-hexene to all. So you can write the compound in those 2 different ways, and that's totally fine. So you've got option A as your correct option. Okay. All right. Next question. What is the correct structure for cis 1-ethoxy to methoxy cyclopentane, which is actually pretty simple, right? So you draw out cyclopentane, and at the first carbon, you've got an ethoxy. So they're testing you to check if you understand what ethoxy is, which is OCH2, CH3, 2-methoxy. At the second position, you have methoxy, which is OCH3. 2-methoxy, 1-ethoxy, cyclopentane, and they are cis, meaning they have to be both can be wedge or both can be dash. It doesn't matter, but they have to be of the same, right? They have to be of the same stereochemistry. So then second option, option B, is actually the correct answer. That was pretty easy, right? Okay. All right. Which of the following groups are considered terminal functional groups? So if you really think about it, aldehyde is always a terminal functional group, right? It's always al. It can always be called as an al. And so it is one of the groups that's actually terminal. If we just had like a group like this, right? Then it is a terminal functional group. And you cannot really have an aldehyde, which is not terminal. You cannot have an aldehyde which is in the center and not in the terminal carbon, because then actually it becomes a ketone, right? So the aldehyde hydrogen has to be there, and that can only be possible if that hydrogen, or if that C double bond O is like the terminal functional group, right? Same with carboxylic acid. Carboxylic acid is C double bond O, OH. So it's only possible to have like the entire group exist only when the C double bond OH is actually the carboxylic acid group is actually the terminal functional group, right? And then the other option is ketone. We know ketone is actually not a terminal group. It's actually in the center, right? So the other option is, this is the ketone. All of these are ketones, but it's never in the terminal. It can never be in the terminal, right? That's why the simplest ketone actually has to have 3 carbon atoms within it. You cannot have anything less than that. So D is actually the answer for this problem. All right, next one. In the figure below, what is the correct name for the molecule shown in the Howard projection? Okay, now for this problem, like what I saw in the textbook, was there's a problem here, right? They have to write these are hydrogens. Because if they don't really write it, they'd be considered CH3s, and this no longer is going to be a glucose molecule, something that they kind of expect you to know that this is a glucose molecule, right? So when the OH group is actually pointing down, right, then it's actually called alpha. The OH group at the anomeric carbon, meaning at the carbon which is right next to this oxygen. So OH group pointing down is alpha, Okay, OH group pointing up is beta. So this is alpha, okay? And then for the to figure out whether this is D or L, if you have a CH2 group which is pointing up, the last group, which is actually the CH2OH, if we were to draw the Fisher projection, there will be like detailed explanation of this when we actually like go from Fisher projection to a ring structure. But for here, when the CH2OH is pointing up in space, it's actually D glucose, but when the CH2OH group is pointing down, then it is an L glucose. So the answer for this is that this is in option A, alpha D glucose. All right, so our next option is the next problem is what is the IUPAC name for the structure below ends with what suffix, right? I love this problem. So what is it really testing us on? It's really asking you, can you identify amongst all of these functional groups, which functional group would actually get the priority, because the one that gets the priority gets to be in the parent chain. And when it gets to be in the parent chain, that is actually the one that's going to be the suffix of the parent chain. Everything else gets to be the prefix as substituents, right? So now if you think about it, this is carboxylic acid. Carboxylic acid is actually the topmost priority of the priority list of functional groups, right? And this is actually more like an ether, right? An ether functional group, alkyne functional group, alkene functional group, alcohol functional group, chloro functional group. All of these are much. This is just alkane methyl functional group. All of these are much later, right? Except alcohol or carboxylic acid is a lot higher. It's actually the first one. So that would actually get number 1. So that is going to be in the parent chain as a suffix. So oic acid is the correct answer. All right, with that, we've come to the end of these problems. And of course, if you want to work with me one-on-one, or if you want to join our summer Orgo program, which is meant for high schoolers or students who are retaking the class or will be taking the class soon in the fall semester, and or want to refresh your concepts for your MCAT, feel free to reach out to me, and I will see you guys on the other side. Bye now.